Section 21 of The Science, History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Fred Abood. The Science, History of the Universe, Volume 1. Edited by Francis Rolt Wheeler. Astronomy. Chapter 14. The Moon. Part 2. As the Moon rotates around the Earth, while the Earth is passing in its orbit about the Sun, it will be obvious that twice in its journey the Sun must come into a line of intersection of the Moon's orbit with that of the Earth. When this happens at the time of full moon, the Earth will lie directly between the Moon and the Sun, so that the light from the Sun is intercepted and a shadow is formed on the Moon's surface. Sometimes the Moon only partially enters the Earth's shadow, and then the eclipse, as this phenomenon is termed, is partial. If, however, the Sun is situated on the line of intersection at the time of new moon, then the Sun will be eclipsed, and a solar eclipse so rich in astronomical significance occurs. Solar eclipses have been discussed elsewhere and their importance explained. Lunar eclipses, besides enabling us to check the motions of the Moon and furnishing an interesting spectacle, afford little scientific information. When the black shadow on the Moon is first detected in the case of a total lunar eclipse, it is interesting to watch its encroachment until the entire surface of the satellite is covered. Even the Moon, on which no direct sunlight can fall, is often visible, glowing with a copper-colored hue, sufficiently bright to enable several of the markings on the surface to be seen. This is due to refraction of the atmosphere, which bends the sunbeams that have just grazed the Earth and permits them to fall within the shadow. In their journey through the denser atmosphere, they have become rich in red rays, which gives to the disk a ruddy or copper-like hue, analogous to that of the Sun at sunrise or sunset. Whether the eclipse of the Moon is total or partial depends on the extent to which it passes into the shadow of the Earth, as the accompanying diagram will indicate clearly. Lunar eclipses are useful to the astronomer for determining the length of the synodic month, and also for determining the temperature to which the Moon has been raised, for when it enters the shadow, all direct light from the Sun is cut off and the Moon becomes cold very rapidly. Furthermore, the position of the Moon with respect to the stars can be determined on such occasions with great accuracy. Like solar eclipses, eclipses of the Moon can be predicted with high precision, and they are regularly announced in almanacs and ephemerides. The Moon always presents the same face to the Earth, a phenomenon discovered by Galileo. It must follow that the Moon rotates on its axis once in the same number of seconds that it requires for a revolution around our planet. This is explained by the fact that tides on the Moon, as in the case of the Earth, have lengthened the period of rotation by their braking action. At a time when the Moon was still a hot, semi-molten mass, the attraction of the Earth produced great tides, not tides of water, but tides of molten rock. These tides on the Moon checked its rotational velocity and eventually constrained the Moon to rotate on its axis in precisely the same period as that which it requires to revolve around the Earth. All this happened eons ago. There is no longer evidence of any tidal action because the Moon is frozen. Although there can hardly be tides on the Moon, yet there may be tides in the Moon. It may be that the interior of the Moon is still hot enough to retain an appreciable degree of fluidity, writes Sir Robert Ball. And if so, the tidal control would still retain the moon in its grip. But the time will probably come, if it have not come already, when the moon will be cold to the center, cold as the temperature of space. If the materials of the moon were what a mathematician would call absolutely rigid, there can be no doubt that the tides could no longer exist, and the moon would be emancipated from tidal control. It seems impossible to predict how far the moon can ever conform to the circumstances of a rigid body, but it may be conceivable that at some future time the tidal control shall have practically ceased. There would then be no longer any necessary identity between the period of rotation and that of revolution. A gleam of hope is thus projected over the astronomy of the distant future. We know that the time of revolution of the moon is increasing, and so long as the tidal governor could act, the time of rotation must increase sympathetically. There will then be nothing to prevent the rotation remaining as at present, while the period of revolution is increasing. The privilege of seeing the other side of the moon, which has been withheld from all previous astronomers, may, thus in the distant future, be granted to their successors. While study of the moon and its motions continued, a beginning was made in the Renaissance to examine the surface of this satellite. Leonardo da Vinci, 1452 to 1519, was the first to explain correctly the dim illumination seen over the rest of the surface of the moon when the bright part was only a thin crescent. This he maintained is due to the earthshine, or slight illumination of the moon by light reflected from the earth, just as moonshine is able to illuminate the earth. Galileo's lunar observations through his telescope were epoch-making. Not only was he able to disprove many common conceptions of the nature of the satellite and its surface, but also to present a mass of evidence of a positive character. In spite of the familiar dark markings, the moon was really supposed to be a smooth sphere. After the introduction of the telescope, however, it was recognized by Galileo that the surface of the Earth's satellite was dotted with various inequalities, which he assumed to be mountains, valleys, and seas. Thus he correctly accounted, in part at least, for the unevenness of the surface. He was not content with mere observation of the features of the moon's surface, but measured the height of some of the more conspicuous lunar mountains, and obtained for them an estimated elevation of 4 miles, a figure which agrees fairly well with modern estimates. Having seen and measured mountains on the moon's surface, it seemed natural that there should be water. The large dark spots he erroneously regarded as seas, although he was not responsible for the corresponding names applied to these supposed expanses of water by some of his successors, and still preserved in lunar maps. The chief marks of astronomical progress, as revealed by Galileo's observation of the moon, were that it was a body in many respects similar to the Earth, that it was not a perfect sphere, and that there is no fundamental difference between celestial bodies and our own Earth, either in their motions or in their general nature, which was important in the final establishment of the Copernican theory. One other discovery of Galileo's in connection with the moon is of great importance. It had been known for many years that as the moon revolved around the Earth, the same markings were constantly seen. With the telescope, these markings could be studied so much more distinctly that it occurred to Galileo to ascertain whether there was any change in the moon's disk, or whether its appearance was always exactly the same. He found that as the moon moves in its orbit around the Earth, that slight changes are seen in its appearance. In other words, small portions of the hemisphere alternately on its northern and southern half are exposed. The simplest of the motions of the moon in this way subsequently came to be known as librations. Kepler, in his epitome of the Copernican astronomy, demonstrated that his planetary laws applied to the motion of the Moon around the Earth, despite irregularities which introduced enormous complications. In this work, however, he devotes much attention to the theory of the Moon, explaining in considerable detail both evection and variation. Galileo established the fact that the Moon was similar to the Earth in many respects. The analogy was carried somewhat further by certain of the pioneer workers with large telescopes. Even Herschel held that because the Moon closely resembled the Earth, it might be a suitable habitat for human beings. The dark spots once taken for seas and bearing that name on lunar maps are, in reality, lava, while the craters which dot the surface of the satellite, with one or two possible exceptions, belong to volcanoes long since extinct. The dark lines once known as rills, which it was assumed were rivers, are plainly without water. If there is a lunar atmosphere, its density must be very small, in fact less than that of the atmosphere far above the Earth. That there is a very rare lunar atmosphere seems to be probable. In fact, the assumption of an atmosphere is necessary for the explanation of certain phenomena. After Galileo's lunar studies, the next important work was that of John Hevel of Danzig, 1611 to 1687, who published in 1647 his Selenographia, in which not only the text but the plates were prepared by him. Here he systematically describes the names and chief features of the Moon, the immense craters and seas, employing many names taken from the Earth, such as Apennines, Alps, and Mare Serenitatis for the Pacific Ocean, all designations still found on modern lunar maps. Not all of his names have survived. John Baptiste Riccioli, 1598 to 1671, in a treatise on astronomy called The New Almagest, 1651, gave to various mountains and craters the names of distinguished men of science and philosophers. Hence the names of Plato, Archimedes, Tycho, and Copernicus are found on lunar maps. These names have survived in considerable number. More modern map makers, such as Beer and Maedler, whose map was published in 1837, and Schmidt of Athens, who published a map of the Moon 7 feet in diameter in 1878, have carried out this idea. Modern astronomers are likewise honored, with the names of various points represented on the maps. For the origin of the Moon, the mind must be forced to look back millions and millions of years to a time when our Earth existed in a very different form. Then it was not a solid mass, but a globe of molten material on which floated a crust, perhaps some 35 miles thick. It rotated not in a period of 24 hours, the present day's length, but at a terrific velocity which may have made the day some 3 hours in length. Such a speed of revolution naturally produced a most powerful centrifugal force. One day a cataclysm occurred. 5,000 cubic millions of miles of matter were thrown off into space. Thus the Moon was born. A great scar was left on the surface of the Earth, a scar which, in the opinion of Professor William H. Pickering, is the basin of the Pacific Ocean. After this rending of the Earth, the remaining parts of the crust, afloat on the liquid interior, were split along irregular lines into two pieces, which drifted apart and were filled by the waters of the Atlantic and Pacific Oceans. This theory of Pickering's is diametrically opposed to that of Professor T.J.J.C., who claims that the Moon is in reality a planet captured by the Earth in its wanderings through space, and that all satellites have been thus captured. Whatever the origin of the Moon, it is the largest of all the planetary satellites, yet smaller in mass than the Earth, from which it is separated by a distance that varies between 222,000 and 253,000 miles. Its gravity is equal to about 1/6 that of the Earth, for which reason the same amount of energy acting, for example, in a volcanic upheaval produced mountains higher than those on the Earth. This mass of the Moon is about 1/80th that of the Earth, or 73 trillion tons. The accompanying diagram shows the comparative size of the Earth and the Moon. The diameter of our planet is 7,914 miles, while that of the Moon is 2,160 miles, so that the diameters stand very nearly in the relation of 4 to 1, while the superficial area of the Moon is equal to about 1/13th part of the surface of the Earth. The average distance of the Moon from the Earth is also fairly constant, and the average fluctuations do not exceed more than about 13,000 miles on either side of its mean value of 239,000 miles. The Moon is essentially a dead planet in the eyes of most astronomers. Its fires long since have been extinguished. It is a great globe of chilled slag. Its craters have no counterpart on the Earth. The lunar crater is a great circular plain, 50 or even 100 miles in diameter, around which rises a precipice perhaps 5 or 10,000 feet, while in the center there may be a hill or two about half as high. Thousands of these volcanoes are visible in the telescope. How these craters were formed is a puzzle. Some astronomers hold that they mark the impact of countless meteorites. Others assume them to be the product of gigantic bubbles in a once molten mass that burst. Again, it is claimed that they are volcanoes resembling those of the Earth. Most astronomers tell us that the craters have long been dead, that the Moon has had for centuries no atmosphere, and therefore cannot have water or support plant or animal life. Professor William H. Pickering, however, tells us of an exceedingly rare lunar atmosphere and maintains that the Moon's craters are not all extinct. He even claims that certain great white expanses are snow and ice, and furthermore, that there is evidence of the growth and decay of vegetation. To support his views of vanishingly feeble volcanic activity, he calls attention to the little crater named Linne, after the famous naturalist Linnaeus. In modern times, this crater has unquestionably undergone changes. Only a few centuries ago, it was described on the old maps as a crater of moderate size, and later as a very small, round, brilliant spot. A dead volcano cannot alter its shape. If there are still a few intermittently active volcanoes, they must expel water and carbonic acid gas, judging by earthly volcanoes. But water cannot be found on the Moon as a liquid, for the temperature of its surface is probably not far from 460 degrees Fahrenheit below zero. Many of the elevated peaks are capped with a silver glow, which also characterizes the lining of the craterlets. In Pickering's eyes, that white sheen is snow. He believes also in accumulations of snow and ice at the poles. If carbonic acid is expelled by lunar volcanoes, it must cling to the Moon with great tenacity because of its weight. Since it is the food of plant life, it may possibly support vegetation on the Moon. Professor Pickering sees in variable dark spots on the planet organic life resembling vegetation. He figures that since certain lichens grow in certain regions of the Earth where the temperature never rises above the freezing point, there is no reason why that vegetation may not flourish on the Moon's surface. End of section 21.